Alrighty, y'all. Today we're taking a look at the recitation for March 25th. And for this one, we're looking a little bit more at the work energy theorem and applying it in 2 dimensions. Right? So the first problem was something that was on Wednesday's recitation. If you didn't get to it, we're starting with it today, but I have the walkthrough for this problem on Wednesday's recitation video, so take a look at that. I'm not gonna do it again. I'm not gonna waste your time. So let's move on to question 2. Right? You have someone swinging from a tree. The swing has a length L, and we have a mass, given mass. Right? Right? And we start at an angle theta, and we have a strong wind blowing from left to right and exerting a constant horizontal force, and it's going to swing further on the right than it started on the left. So now let's set up our work energy theorem. So we have to write our equation moving from A to B. So labeling in words what each term represents as well. So the first thing we're going to start with, our initial mv, and then since we're starting at A squared, our initial kinetic energy plus all of our work done equals our final kinetic energy, which we're ending at B, so I'll label that there. So now we have to think about what work is being done to the swing. So if I'm thinking about my swing force diagram here, I'm gonna just line it up as if we're at point A right now. Acting on the swing, I have gravity, right? And we have the tension of the rope holding onto the swing, and we also have this force from the wind. So we have 3 forces. So now let's think about the work done by each. Gravity, work from tension, and work from the wind. All right. So now let's think about each one. So gravity is going down. So if we're doing our equation for work, which is our force vector dotted with our displacement vector, right? G. We have to get our displacement that's in the direction that G is. So G is acting in the Y direction. So let's find our displacement in the Y direction. So we're going from here down to here. So this is going to be our displacement in the Y direction. Well, how do we get a number for that in terms of things that we know? Let's take a look at the geometry of it. Right? So I'm just going to borrow this as I'm just going to pull some of the other things with it, but it's fine. I'll just erase them. So we know the rope isn't changing length. It's always going to be length L. And we know this theta. So I'm going to make my right triangle here. Okay? And remember, I'm looking for this height because that's our displacement in the Y direction. So what I'm going to do is I'm going to have my trig for all of this because I have the length of the rope. We can't say that this is L because this is really what is L. So we have to just set it as the hypotenuse, break it into pieces to figure out what this piece is so we can subtract and get this piece. Okay. So if that's L, this is going to be L sine theta. This is L and this big bit here. Right? Not L. L cosine theta, right? Because it's adjacent. And now that means that if this whole thing's L, we have this little piece that's L cosine theta. This is going to be L minus L cosine theta. Right? So now we have a displacement in the Y for our G and our force from gravity, our mg. So now we just think, is it positive or negative? So gravity is going down. The displacement is also going down, so that means gravity is doing positive work. So we have mg times L minus L cosine theta. I'm mixing up which one's which already. So now let's look at our work done by tension. So our tension is pulling us in the this way direction. Okay. So as we're swinging, I have to find out what our displacement is in the tension direction. Well, as we're going, tension's always pulling towards the center of the circle, but we're never moving towards the center of the circle. We're only ever going tangent to the circle. So we're not moving in the radial direction. We're not moving towards the center of the circle at all. We're going around it. So we're not really moving. It's not that we're not really moving. We're not moving in the tension direction. So our work done by tension is just going to be 0. Now we get our work done by the wind. So we're given our force, Fw over here, right? And now we have to do the same thing we did with gravity. We say that here's our wind acting in the x direction. Now I'm going to say from here over to here, there's our x displacement. So let's figure out what that is. Right? It's going from like the bottom of this corner over here directly across. It's that distance. It's going to be this distance, which we said was our L sine theta. So I can say that this is our force from the wind times our L sine theta. And again, just thinking about which direction our displacement's going. It's going to the right, and our wind is also pushing to the right, so this is also a positive work. And since we're starting from rest, right, we pull the swing back, we hold it there, and then we just release it. We're not giving it an initial velocity. Our velocity at A is 0. So that's just going to go away. All right, so now let's write our revised work energy theorem. We have mg L minus L cosine theta plus Fw L sine theta equals our final kinetic energy, 1/2 m BB squared. And I'm not going to write it out in words, but it says talk about in words, here's our work from gravity, our work done by the wind, and our final kinetic energy, our initial kinetic energy. Again, just breaking it into these pieces and smushing it all together. All right. Now we're finding our speed of the swing at position B. So it's asking for the speed, so that's going to be the magnitude of our velocity, which is what is in this equation. So let's take this equation and do some math with it. Let's solve for VB, because it needs to be in terms of Fw, M, L, and theta, and G, which all of this already is. So we're just going to solve for VB. It's just algebra, so I'm going to distribute this in and then factor out the L. So L comes out, and then it's going to be mg minus cosine theta, minus mg cosine theta, minus mg cos theta, plus force of the wind, sine theta, and I'm going to multiply by 2 on both sides, and divide by m on both sides, and that equals VB squared. Right, so simplifying this a little bit more, I'm going to put the m in the parentheses, so it's going to be 2L G minus G cosine theta plus Fw sine theta, since this one didn't have an m term to get rid of, just goes right there. And now I'm just going to square root both sides to give us our final velocity at point B. There you go. So now we need to solve for the angle in terms, now the other angle over here, this phi, whatever we're going to call it, phi, fo, fum, I'm going to call it phi. We're going to solve for this angle in terms of all of our variables. You need some trig to actually like isolate it and say phi equals an expression. So we're not going to do that. You need some like trig identities to do that. We're not going to go all the way there, but we're going to get the equation all set up to think about it. So I'm going to start where we started before. So I'm going to start at point, I'm just going to start from the beginning, pick 2 points. So I'm going to start at point B, and then we're going to point C. So at point B, we have our 1/2 mvb squared plus all of our work, and that has to equal our 1/2 mvc squared. So now we think about, again, what work's being done. It's the same three forces, so we're going to have think about work from tension, from the wind, and from gravity. So let's look at those work. G, T, and wind. Okay. So our work done by gravity, right? Gravity's still pulling down, but now we have to think about our y displacement because we need another value for that. So I'm going to, again, pull my little, oop, I didn't want to bring that arrow. I'm going to pull my geometry down here to look at it a little easier. And I can say here's L, and I'm now looking for my, this way, we're looking for this. That's going to be our height, that's our H. So here's our B. So if up here is going to be L cosine phi, it's going to be L minus L cosine phi, and this is going to be L sine phi. Okay. So we're looking at our force due to gravity times our displacement in the gravity direction, which is this chunk down here. But now, if I look back at the top, right, before we were going from here, we're going down. Now if I extend these lines and look at it up here, I'm going from, I drew this line a little low. I guess I drew it low before too, either way. But now we're going from down here up. So now gravity's going down and our y displacement's going up, so it's going to be negative. A negative mg, and then we said it was L minus L cosine phi. Oh. Now, by tension, work done by tension, it's the same thing as before. We're not going in towards the center of the circle, we're just going around it. So our work done by tension is going to be 0 again, because we're not going towards the center of the circle. All right, now our work done by the wind. Same thing, same kind of thing that we said before. Our wind is going horizontal, so let's get our x displacement. So if I'm here, I'm going like that. There's our x displacement. So let's go solve for that with our triangle, which we already did. We have our L sine phi there, and that's going, wind's blowing to the right, and our displacement is also to the right. Oh, sorry, the wind is blowing to the right. This is our wind over here. And our displacement is also to the right, meaning we still have positive work done from the wind. So that's going to be force from the wind times that, we said it was L sine phi. Okay. So now let's get everything all plugged in. We're going to say that it's 1/2 mvb squared plus force by work, L sine, force by work, force by wind, sorry, I've been writing W for work, forgot what it was, minus mg, L minus L cosine, that definitely looks like an L, cosine phi, and that's going to equal our final kinetic energy. All right, so now we have to think about what else we know in this equation, because we just want it in terms of our force, mass, length, theta, and g, right? We know we can figure out our velocity at the end is when it goes to a max height. So that's like when we started, that's going to be a 0 velocity, because that's when it's going and it's turning around. So our velocity is 0, our final kinetic energy is going to be 0. That one just goes away. And we just solved for our velocity at b, so we can just plug in our expression up here for that, because that's because we're looking at this, it's the same situation, just later down the line, right? So I'm going to borrow this, right? And since it's we need v squared. I'm not going to bother bringing the square root down and re-squaring it. So here's our vb squared, plugs in for vb squared. So it's that, and I multiply by 1/2 m, that plus wl sine v, and just to make everything positive, I'm going to take this negative mg and bump it over to this side. Just so it becomes positive, it makes it more pleasant to look at. Okay. All right. And in real life, obviously, I'd be looking to like solve for, that says this, yes, this should still be theta. Sorry, I thought I wrote it wrong for a second. But no, these should still be theta because these are from the original, dependent on the original angle that we pulled it on from. So yeah, this is our equation. Obviously, in real life, you could solve for this or make a graphing calculator solve for this for you, and you you get isolate phi and figure all that mess out. I'm not going to do that. That's just algebra. I trust y'all to be able to solve an equation. I believe in you wholeheartedly, so we're going to move on to the next part. Okay. So when the tire swings back to the left, will it stop at position A, go further than position A, or not make it at all? So when we're looking at this, we start over here, we swing all the way over. Now we're trying to figure out whether or not when we swing back, we make it all the way to A, or if we go further, or if we don't go as far. So let's think about this, right? As I am looking at all of this, our thing from before, if you remember the box problem, we pushed the thing up the hill with my state 1 and state 2. When it came back down, when we did have friction, when it came back down, it was going slower. But if we ignored friction, it was going the same speed when it came back, because whatever work was done by gravity in the negative direction going up, it was just undone again going down. We can say the same thing about gravity in this case, right? Because as we go up over here, gravity's doing some negative work. Then we come back down and gravity's done positive work, just opposite magnitude. Sorry, opposite direction, same magnitude. And the same thing is for this wind force, because it's always going to be pushing to the right. So as we go this way, we have positive work done by the wind. But if I'm swinging back this way, I'm still swinging the same distance. I'm just now going to be having that work undone. So it's going to be same magnitude, but negative work done by the wind coming back this way. So if I'm going the same speed as I was before, so we said all the energy from here, we did the work. Now it turned into kinetic energy here. And then it became, there was more work done, and there was no more kinetic energy here. Then we do some more work, and we're back to the same kinetic energy that we just had. All the energy states have to be equal. So if I'm still swinging, it's still going to do the same magnitude of work for both directions, just opposite what it did the first time. So we're just going to swing right back to where we started. Really is the moral of the story. It's because all the forces are conservative, meaning they don't, whatever they do going one direction, they undo going the other. Right? That was not the case for friction when that's a non-conservative force, because if I go in one direction, friction is opposing my direction of motion, but when I come back again, it's still doing negative work on the object. Friction was, for the situation, was always acting opposite the displacement, always doing negative work, but this one switches direction based on which direction I'm going. So now we're looking at work energy in terms of climbing a mountain. So for this one, we're going to be looking at whatever this mountain is. We start the hike around 1650 meters, and we end around 2850 meters. So we have some displacement that we're going. So I'm going to say, thinking about what's going to happen for our work energy theorem, just to simplify things, I'm going to say that my hiker starts by standing still at the bottom of the mountain, and then when they get to the top, they stop for a minute and look at the view, right? So I'm saying my initial and final kinetic energy are both going to be 0, because I've decided this. Because that simplifies things, and yeah, so we say our initial and final kinetic energy, or at the very least, we don't care about our changing kinetic energy, because we can stop and start and slow down and speed up as all we want, but really what we're looking at is the energy required for us to physically go from here to here, right? So we have to think about the work done on our hiker. So we have, since we're saying our change in kinetic energy is 0, or it doesn't matter, whatever it is, now all we have is our work. So all of our work we have to figure out what's going on with that. So all in all, and in the end, we have gravity work pulling us down, and really our legs are doing the work to push us up the hill. It's more of like there's friction and we're pushing against the ground, whole mess, whole everything, but really we have to use our legs to exert some kind of force to move us up the hill, up the mountain. It's not a hill, it's a mountain. So really the way we can think about it is that, right, our work done by gravity, since we're going up the mountain, gravity's trying to pull us down, we're going to say that's a negative mgh, where our h is going to be the difference between these two. We'll solve for that in a second. And our mechanical work done from our legs, I'm just calling that work L for legs. So the mechanical work that we need to make sure that we're not losing altitude, I guess. The mechanical work we need to oppose gravity in this case is going to be the force from our legs times that same distance, right? Because effectively, our legs are just pushing us up. For our intents and purposes, our legs are pushing us up, and we're just going to multiply it with the height. So we don't have to think about this just yet, but because we're just solving for this mechanical work. But either way, this is what we're going to be thinking about later on if we need to solve for the force that our legs are exerting or something. We're not talking about that. So now if we set up our equation, we're going to say that our work from our legs, which we said was positive, minus our mgh equals, and we said all of our kinetic energy changes, just is 0 just to simplify things. So now we just estimate our mass, and then we can solve this and estimate the work required for our hike, our adventure. So our h1 minus h2, that's 2850 minus 1650, right? Oh, I didn't solve this one all the way out. I didn't punch this into my calculator. Either way, we can estimate, we estimate our m. I said a person with gear, just to keep it a round number, I just said mass was 100 kilograms. It's probably not that much. It's probably maybe closer to 70, but this is easy to estimate with if I don't feel like punching things into my calculator, which I guess I didn't feel like punching things into my calculator. So either way, we can solve this, and really our work done by our legs is just going to be mgh. Those are all known values now because we made an assumption about one of them, and now we get to figure that out. Now, how many joules of chemical potential energy must be metabolized? So our work required is what we just solved for, our mgh. So we look at our efficiency of how much of what it gets metabolized is used mechanically, right? So we have an efficiency of 20%. meaning that 20% of the energy metabolized, so 20% of whatever we need to metabolize, so our chemical energy, so I'm going to call it whatever, UC for potential energy chemical. So 20% of that is what's going to be used by R, be available to us to use for climbing the mountain. So 20% of this is that. So if I just multiply this by 5, I'm going to say that UC is 5 times this, because this is really 0.2 percentage. We just multiply by 5. That's how much we need to metabolize in order to produce this much mechanical energy. This is the mechanical energy we need, so we need to metabolize 5 times as much as we need so that we have enough. Now we do some unit conversions. This is, pretty much we do the same thing where we have our how much chemical potential energy needs to be metabolized, 5 of that, and they have to how much kilocalories from food. So this is going to give us an answer in joules, and then whatever we get our answer, we're just going to multiply by 1 kilocal is 4180 joules. So since this is equal to this, technically I'm just multiplying by 1, but it's getting rid of that joules. So I'm just dividing by 4180, and that's going to give me my answer in kilocalories, which I also did not punch into my calculator. All good. So an apple being about this, Cliff Bar, all of this, I guess the amount of food you expect the hiker to use, that depends on your previous answer. So really it's 100 plus 250 plus 400 equals 750 kilocalories. And if this is roughly this, they're roughly the same, and again, because since we made this estimation up here, they might not be exactly the same, or they might not be, like, we'll make a rough estimate and say we want to supply as much food, more food than we use, but it's again, it's all an estimate. And how much heat will the hiker's metabolism produce? This one, we're going to come back to our efficiency. So we know that 20% of the chemical potential energy that gets metabolized is used for mechanical work. So the rest is going to be released as heat. So whatever we have for our 5 times our mechanical work required, that's our chemical potential energy that gets metabolized. So now we're just going to take 80% of that, because that's like the remaining is times UC, and that's going to give us the amount of heat produced by the hiker's metabolism during the course of the thing, because we have 20% going to mechanical work, 80% going to heat. And now the same thing, going on and using this number that I didn't calculate. We're talking about evaporating, how much sweat we need to evaporate in order to keep sufficiently cool, and how much water we need to drink. So if this is the amount of heat being produced, so we figure out how much water gets evaporated. Right? So this is in joules. We divide by our joules per milliliter of water. So we say whatever our 0.8 times UC, we're going to divide that by 2,500, because that's going to give us how many milliliters of water we can evaporate. Really, because we're doing 0.8 UC joules, and we're multiplying by that being 2,500 joules per 1 milliliter of water. So that gives us milliliters of water are going to be evaporated. So now that we're in milliliters, that's how much water we need to drink, because we need to be replenishing all the sweat that gets evaporated. So we punch this in, and that's going to give us milliliters of sweat, and that's going to be the exact same as how much needs to be replenished by drinking water. So milliliters of sweat is the same as our milliliters of water, whatever answer that happens to spit out. When I took 211, this is a bit of a tangent. The recitation's done. You're good to. But when I took 211, I finished this. I overthought this problem a lot, because my brain said, well, if this is based on my MGH, right, my mechanical energy is based off of my mass. If I'm drinking water and evaporating off sweat, then technically the mass is also changing, right? Because the mass is, like we said, it evaporates 1 gram of water with the milliliters. So that's technically changing the mass of our hiker, meaning they have to do less work, meaning that they can drink less water. However, that is outrageously overthinking it. And technically, though it is technically true, the rough estimate we made for our mass is already producing more error than ignoring this would. So we're ignoring that because it doesn't change too much, and also like 1 gram in the scheme of like our 100 kilograms is almost nothing. But yes, we're ignoring that. But if you were thinking like, oh, doesn't the mass change? That's what I thought when I first saw this problem last year. But we ignore that because it's all estimations and it's fine, it doesn't matter. It doesn't affect things too much. Anyways, I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this recitation or any other problems that you want me to try to explain. And I'll do my best to try to explain them, because I guess Sydney explains stuff.